As you can see, we have a little bit more difficult of a problem to work with. And the first reason why it's more difficult is there are 3 resistors instead of 2 running in parallel. And the second reason is we have these way bigger resistors. So that 470 ohm resistor is actually the smallest one because these two are kilo ohms. So 3.3 kilo ohms becomes 3,300 ohms. And likewise, 2.2 kilo ohms becomes 2,200 ohms. And to solve this entirely, we need to find several things. The first one is, of course, the resistance total. Then we need to find the total current, and we need to find each individual current for each individual resistor. And since this time we have 3 resistors, we have a current 1, a current 2, and of course, a current 3. And so quite a few things to solve for, but my goal in this video is to show you that this actually isn't really all that hard. It's just a little tedious, a little time consuming, but it's a lot of just plug and chug. So let me prove that to you. Let's start with our resistance total, and to do that, we will go ahead and use our inverse resistance total equation. That's 1 over RT equals 1 over R1 plus 1 over R2. And since we have 3 resistors, we'll add an extra one, 1 over R3. So it doesn't change our equation all that much. Like I said, we just plug them in. 1 over R1 is just 1 over 470, plus 1 over R2 is 1 over 2200, and then 1 over R3 is just 1 over 3300. And don't let those numbers scare you. There's actually a really easy way to solve for this, and that's actually using our calculator, this button right here, this N over D, which stands for numerator over denominator. If you hit it, it allows you to type in a fraction. And so we can actually write 1 over 470 very easily. Then we can leave it and hit the plus button, and we can do it again. And so you can see there's actually a really easy way to plug this into our calculator and solve this equation super fast. So we do it one more time, plus numerator over denominator, we write 1 over 3,300. So I love this feature in our calculator, and you get to use it in the class, which is nice. We hit enter, and we get this weird number, this 0.00, so 0.0028885, and then it continues on. And if you're thinking to yourself, that's a weird number, how could that be our total resistance? You're right, that is a weird number. It's not our answer. That's the inverse of our answer. So to solve for our actual resistance, what we're going to do is we're going to take the inverse of that. So we just take that to the -1 power, which is actually really easy in our calculator. We have a button for that. It's right here, this x to the -1. It means take whatever our number is to the -1 power when we hit enter. And sometimes you'll get this really weird fraction when you use this feature. That's just the exact answer in fraction form. We can easily convert that to a more friendly version of the answer, which is decimal, by hitting this button right here. And we get 346.59 ohms for our total resistance. And let's think about that answer for a second. This answer actually makes sense, that we would get a total resistance smaller than each individual resistor, because in a parallel circuit, we are actually improving the total current by lowering the total resistance. So that's a good way to double check your answer in a parallel circuit. If you are getting a total resistance bigger than your individual resistors, then you know you're wrong. It should be smaller than each of your individual resistors because we've improved the total current. And speaking of the total current, let's go ahead and solve for that one as well. The formula hasn't changed. It's just voltage divided by resistance. And since we are using the current total, let's go ahead and use the resistance total. And so then that's really easy. We know our voltage is 15 volts. And as you can see, all we're doing is just plugging in our numbers. So this super scary looking problem is actually really easy. It's just a bunch of plug and chug. And so we just pull out our handy dandy calculator and we type that in, 15 divided by 346.59. And what do we get? We get and uh-oh, I actually typed that in wrong. And there we go. That's actually typed in better. So what do we get? We get 0.04327, so we get equals 0.043, let's just round that off at 0.433. And we can actually, well, let's write amps. We can actually rewrite this as 43.3 milliamps if we want to. And all we did to do that was we just moved that decimal 3 places. Pretty simple. Nothing new there, and just remember that they're the same answer. They both mean the same thing, but one is one we use in math and one we use on labels and in conversation when talking about these circuits. So pretty easy. And then current 1, current 2, and current 3 are all just as easy. We just use voltage divided by resistor 1 since it's the current running through resistor 1. The voltage is, of course, constant. I can't stress that enough, so we keep using the same voltage. And then we know the resistor one we've known since the beginning of the problem. So that's 470 ohms, and we just typed that into our calculator. And if you're wondering, well, Mr. Anderson, could I have solved for the individual currents first? The answer is yes, very easily. What do we get when we type that in? We get 0.0319, so we write equals 0.0319 amps. And of course, we can write that as 31.9 milliamps. And we'll do the exact same thing for current 2 and current 3, and as this is getting easier, we'll pick up the pace a little bit. We know the voltage is still 15, and we'll divide it by resistor 2 for current 2, which is what, just 2200? And if we type that into our calculator, what do we get? We get 0.0068, so we can write current 2 equals 0.0068 amps, or of course, we can change that to 6.8 milliamps. And then we can do the exact same thing for current 3. The voltage hasn't changed, and we divide that by our resistor 3, which is 3300. And what do we get? We get 0.0045, so we can write that out as well. Current 3 equals 0.0045 amps, or of course 4.5 milliamps. So we went kind of fast there at the end, solving for the individual currents, but hopefully that's because it's just way too easy, way too obvious to solve for these because it's just plugging them in. But if you look, actually there's the coolest part about parallel circuits, in my opinion, is a way to double check your answer in the end. You can see if these individual currents add up to your total current. And if they do, we know we got our total current correct earlier when we used our resistance total to find it. And if our current total is correct, then our resistance total is probably correct as well, because that's what we use to solve for it. So it's actually a really cool way to just double check your work in the end of the problem when dealing with parallel circuits.